Hello. Hello, everyone. I'm Susan Nash, and I'm thrilled to be here today with Critical Minerals Focus. We have the Energy Minerals Division in the spotlight today with Ashley Douds, who is our current president, and Aaron Ball, who will be he is our president-elect, and he will be our incoming Energy Minerals Division president. So today's focus is Critical Minerals Uncovered, New Trends and Tools in the Hunt for Rare Earth Elements. And this also includes lithium, so that even though that's not technically a rare earth, it includes lithium, and Aaron will focus on that. And I just want to say ahead of time that um, we are having some technical difficulties with Aaron's audio, so it's possible that we will have to record his part at a later date, but we're going to go for it when it's his turn. So we'll just a heads up. So anyway, and just a note that you will get a copy of this presentation in the form of a link. We will email you the link, and then if you are a current EMD member, please do a little hands up or thumbs up or something. Let us know in the with the reactions, because I'd love to know if you're an EMD member. If you are not, please right now consider joining. It does not cost any money, and it's very easy to do. All you do is log into your AAPG account and check that you'd like to join EMD. Now, if you are not an AAPG member, I would like to encourage you to apply right this minute because you will be amazed at all the different benefits, and we are currently at this point adding even more benefits that will be unleashed, if you will, in within a few months. So thank you for being here, and I would like to invite Ashley Dowds, who is a research geologist at Indiana Geological Survey and at the Indiana University at Bloomington. So I'd like to invite her to join us.
Hello, can you all hear me okay?
Perfect.
Okay, good. Thank you, Susan. Really happy to be here with everyone today. Happy that you could join. Like Susan said, I hope that everybody is a member of EMD, and if you're not, please consider joining. Actually, that's going to be my first slide, if I can page down. I just wanted to give a quick overview to everybody about how the committees have been restructured over the last year. An AAPG Explorer article that I wrote at the beginning of the year kind of went over this, but just really briefly wanted to, give an overview of what we did and why. There are three committees that did not change, and that would be the Geothermal Committee, Hydrates Committee, and the Energy Economics and Technology Committee. You can see, on LinkedIn, Geothermal Committee is very active. I hope that you are following them on LinkedIn. The Hydrates and Energy Economics and Technology Committees have recently provided an annual update, and that's on the EMD website as well. So really, there were three committees that were kind of involved in a reorganization, if you will. We had the Tight Oil and Gas Committee. We noticed that the membership was kind of going in a different direction. And so we decided to kind of divide the components of the Tight Oil and Gas Committee and move it into either the Geologic, Hydrogen, and Helium Committee or Critical Minerals and Uranium Committee. So the basic division would be anything that's a gas at the surface goes into the Hydrogen and Helium Committee. And so that would be from the Tight Oil and Gas Committee, that would include, gasification of coal to generate methane and hydrogen, coal bed methane, tight gas sands. Those are now all within that committee. And then for the Critical Minerals and Uranium Committee, those are focused on, extracting material from rocks and liquids. So essentially, we have brought in critical mineral extraction from coals and coal byproducts, bitumen, heavy oil, and tar sands. And then also we have a new focus area, which is produced water, which I'm pretty excited about because we do see that the membership is pretty active in that. So it only made sense to make sure that we had that focus area within the committee. So those are the committees that we have right now. Anybody that's interested in joining those committees, please feel free to reach out to me or, of course, Aaron, who is our upcoming president, and we can get you in touch with the right people so you can be a part of those committees. So on to the presentation. The intent for this presentation is really just to provide a very broad overview of what the potential energy mineral related activities are that I'm seeing in Indiana and the Appalachian Basin and the associated data sets that are really fueling that. So I'll give a very brief overview of the new publication from the USGS on geologic hydrogen and how that potentially impacts Indiana. Looking at unconventional sources of critical minerals and rare earths. I really want to focus on the funding mechanisms, the evolution of those funding mechanisms, and our understanding how those have evolved with the changes in the focus of the funding mechanisms. And then just really briefly talk about techniques that the Indiana survey, as well as other surveys and industry, is applying to gather more information from these existing data sets because those are so valuable. But in general, the theme that I want to get across here is the importance of the pre-competitive science and publicly available data sets. So the pre-competitive science would be anything that isn't really in the industry realm, or maybe if it is, it's kind of proprietary. But as publicly funded research institutions, that pre-competitive science becomes something that is shared with the public and becomes a very valuable tool. So for those of you not familiar with the geology of Indiana, I just wanted to give some really high level bullet points basically about some of the unique geology in Indiana. I spent most of my career in the Appalachian Basin and in Texas, Permian Basin, offshore, and Indiana really has some unique stuff going on. Starting at the very deep stuff, we have faulting down here, the very deep Wabash Valley Fault Zone. Associated with the Reelfoot Rift that's down to the south. We also have a rift zone, a failed rift over here, the Fort Wayne Rift, that can be seen on gravity maps. And that just kind of cuts the northeast corner of Indiana over there. You're probably all familiar with the saline reservoirs of the Cambrian and Ordovician, specifically reservoirs like the Mount Simon. These have been wastewater injection intervals and also, really deeply studied for carbon sequestration for decades now. Down here in the Illinois Basin part of the state, you can see we have oil and gas wells down here, mostly within the Devonian, Mississippian, and Pennsylvania intervals. And then we have this very large field here in the east central part of Indiana, the very old Trenton field. Highly drilled, just an amazing amount of wells in that interval, pretty shallow. But this was developed, in the late 1800s. So really started as an economic power horse for Indiana. Other things that we see in the subsurface geology include indications of fluid flow. So in the Ordovician dolomites, there's a lot of vuggy porosity development. And we also have indications of minerals like sphalerite that occur throughout Indiana that indicate that there were Mississippi Valley type fluids that were transported through the area. Down here, overlapping with the oil and gas productive areas are areas where there's coals. So there's a lot of coal mining in the state, which leads to some of the coal waste that is being analyzed in the state for critical minerals and rare earths. And then finally, we have an impact feature, which I was surprised to learn about, but right up here in Newton County, this little bullseye right here on the map is an impact structure that has some really unique geology that, in my opinion, is understudied. So going over this publication from the USGS that came out recently, just really amazing amounts of information in there. And what I have been focusing on is their information regarding the sources of geologic hydrogen and how maybe they are distributed throughout Indiana and what maybe the opportunities would be. The three main areas of sources that impact Indiana include serpentinization, which is the reduction of water by oxidation of iron-containing minerals, mostly associated, they are associated with ultramafic rocks, radiolysis, and then deep sources of hydrogen. So if we look at the distribution of potential areas of serpentinization, you can see that the Fort Wayne Rift does show up on this map. So the potential is that ultramafic rocks are, a bit shallower and can have interaction with water potentially to generate hydrogen in this area. Note that this is not a productive oil and gas productive area of the state. So there's not a ton of information on gas composition there. Radiolysis, you can see that it's associated with granites and granitoids of the North American craton. So there's a pretty large area that covers. And then deep sources. So these are really interesting. These are, there's some kilometer depth scale surface faults that have been identified here on the map. And then also there's these suture zones that again go right through Indiana as well, where you have lithospheric boundaries that could promote fluid migration from depth. So these are the very deep sources of hydrogen. So a lot of the areas where we see that there's potential, we don't have a lot of oil and gas exploration or development in the past. And so that leads to what I see as kind of sparse data as far as understanding if there has been hydrogen or associated helium generated in those areas. So this map here, I don't think that there is anything in Indiana, or it was just not notable to show up on the map. In the helium map, you can see that there are a few points in Indiana, again, mostly focused where there is oil and gas production. So that does leave a pretty big void. We don't have necessarily a lot of wells outside of those oil and gas productive areas, but perhaps there needs to be some soil gas sampling. Seems like there's some opportunity there to maybe validate some of those things on the map or see if those sources actually are active in that area. So kind of switching gears now. Now I want to talk about kind of the evolution of how data has been collected and the funding mechanisms for them. Really, we have two buckets, two initiatives through organizations like the USGS and the DOE that have, consistently over the decades funded for pre-competitive science so that we can really have this foundational information that we have today for understanding critical mineral and rare earth element distribution in these materials. So I kind of view it as the USGS funds kind of the raw geologic material. That would be the coals, the shales, the paleosols, the rocks themselves. And then the DOE is interested in understanding those distributions within waste materials. So the coal byproducts, the produced waters, and even something that I hope is on the radar, which would be drill cuttings, because those are also a waste product that could have some potential. So if I kind of walk through the ways that the data have evolved here at Indiana, this is kind of the data sets that are publicly available here. Like I said, there's been a lot of funding through the years, especially associated with the USGS and pre-Earth MRI. This is the Indiana Coal Quality Database that is available online. And you can see within the coal region all the data that have been collected and are available. This is updated as new information becomes available. But really the focus of these data points is more on the majors. So the aluminum oxides, the iron oxides, those major components of the rocks, and maybe less so on the trace elements. But as things, as the work progressed and as things changed on what the concerns are, there is this paper from 2007 where the focus was really on elements that are of concern from an environmental aspect. So the arsenic, cadmium, lead, and zinc content of various economic coals. In this case, it's the Danville and the Springfield. And so this information, is really useful. It's interesting to see the ranges of elemental concentrations relative to the U.S. coal averages and the Earth's crust. So there are some pretty high numbers out there. Moving on to kind of the next phase, which in my mind is, the dual support of Earth MRI and Core CM, where we're not just looking at the raw materials, but now we're also looking at the coal waste for, the focus being on the critical minerals and rare earth content, because that becomes, a pretty heavy focus for funding. And what you can see here now is that, Maria and her co-authors have done amazing work at relating these values like aluminum content, which again is something that we have a lot of in our pre-existing databases, to gallium. And so by looking at those relationships on specific samples, coming up with this pretty strong relationship between aluminum and gallium within the paleosols, then we have the ability to go back and look at those data sets that didn't have gallium content and maybe make some indications of where we should be focusing the effort so that we can understand which areas to really focus in on. And then, of course, next is rare earths, and that's really rare earth element concentration in these coal byproducts is really a big focus of a lot of the funding that's going on now. So again, a similar type situation where something like aluminum that is, very frequently collected in these data sets is plotted next to the rare earth total concentrations to come up with these relationships. And then we also see that is the same thing for acid mine drainage, because of course that's another material that could be cleaned up with the right technology applied. And so all of that, all of those data sets that have been collected, all of that information, it's so valuable because not only can we develop these relationships so that we know, so that we can predict where maybe the higher concentrations are, but then that also informs how extraction should be focused, how it should be targeted. So for instance, with the gallium in the paleosols, we saw that it was associated with aluminum content. So it's associated with the clays most likely. So that means targeting those clays for extraction of gallium and understanding how to separate those products is the best place to kind of spend that time. So in the state of Indiana, that's actually become, a pretty big focus. An executive order was issued, and now, the impetus is to find where these concentrations are highest and how to extract them. So, that all those decades of work have now led to this moment where we see that there's of great interest to look at look at all this data in the state. So now switching to shales. Again, we see critical mineral concentration is concentrated in these. This is mostly focused on the metals. So this paper here focuses on the organic rich Pennsylvania black shales. And you can see that these metal concentrations are fairly enriched relative to the upper continental crust for a lot of these metals, which means that these shales are potentially places to look for where we can see those highest concentrations and how to, go after extracting them. So from my days in the Marcellus, we saw these same things, and for me, this light bulb came out of all of the XRF that was being used for geosteering. So, as you started to look at how these concentrations were changing along the wellbore and also in a stratigraphic sense, it became pretty clear that this is something that is worthy of looking at. And, I think in the beginning, a lot of people were concerned because they were just thinking about the vertical thickness of these shales and, potentially not being able to get much out of them. But remember, we're drilling these really long laterals, right? So you have a lot of cuttings that are coming out that, it would be great to understand how to extract some of those metals from the cuttings, which again is a waste product. Not only that, when the wells have completed production, you have a wellbore sitting there that has a lot of surface area contact with the rock, and all those fractures go even deeper into the rock. So how can you potentially, liberate some of those metals for beneficial use? So with all that information, I was working with my colleagues, Randy Blood and Scott McCallum at Wildlands Research, and we did a study on the Upper Devonian Dunkirk Shale Formation. It was, us wanting to really understand that stratigraphic variation of these metals relative to the facies that we see in the outcrop. And so this is kind of this is the outcrop. These are the outcrops that we looked at. Randy had a backpack drill that went out and collected these cores, did XRF and XRD. We had a lot of partners on this, and it's a really great study. Some of the output included, again, that relationship between those majors like iron and aluminum, and some of the metals that, we don't have quite as much information about. So in this instance, you see we have aluminum versus lithium. And by looking at the different facies and how they vary, we can see that the gray shales actually have the highest concentration of lithium within this data set. And so again, it's most likely associated with the clays. And then when we look at iron content relative to specific metals, we see that some of the intervals that have higher pyrite concentrations do have more metals associated with them. So using those types of relationships, you can then build calculated curves. And these calculated curves really just give you a generalized sense of how things are changing stratigraphically. But that becomes really important because you can identify them by facies. So here you see the black shale, the gray shales, and then these pyritic lags within the interval and how it relates to these different concentrations. So that becomes a very powerful tool. It's not it's not the final number, but it gives you a sense of how these things are changing, and gives you a better way to kind of map it. So this using something like PXRF, that is just such a valuable tool that I think a lot of surveys and a lot of industries are using to collect all this various information in a very rapid way, and then being able to apply that to the data sets that are more expensive, harder to collect, take longer to do. And so what we've been doing here at the Indiana survey is collecting PXRF information on some of our cuttings. We have these lith strips. That's what this is over here. And basically what it is when operators turn in their cuttings, 10-foot samples or maybe even 20-foot samples, depending on what they submitted, are glued onto this cardboard at the depth interval that they're labeled as. And then we can quickly, gather that PXRF information and have that information for the entire stratigraphic column rather than just the chord interval, whatever chord interval, was the target of the operator. So that becomes very valuable for not only, understanding potentially what the variation is on those critical minerals throughout the interval, but also making petrophysical models. Like there's really a lot of great information that can be used with that PXRF analysis. And then the last thing I wanted to touch on was the Kentland Dome. Again, very unique feature here in Newton County, Indiana. Here is a close-up of the very complicated geology that we see. And these red dots here are the cores that we have in our core library. And so the idea was that we should go through, kind of clean up our inventory. A lot of these boxes just had a couple inches in them, and potentially analyze them for critical minerals. We're in the process of doing that right now. And the reason that it is so unique is you can see that these rocks have undergone tremendous pressure and temperature changes, which is not something you really see in Indiana, but very localized, vertical fractures with fluid-filled fractures that precipitated minerals in them. And then, almost like metamorphic textures in here. So these rocks have really gone through a complex history, and, gathering some information on their critical mineral content, I think, is a really interesting idea. And so I wanted to also bring up the Continental Scientific Drilling Facility at the University of Minnesota. So this is a group that really is doing some fantastic work on understanding what the needs are for things like the energy transition. What are the data sets that need to be collected? What are the implications of those data sets? And, this is really a way to inform how we go forward with developing these subsurface energy systems. One of the things that is kind of talked about in this working group is the potential for public-private partnerships. I think that's come up a lot here recently. And does that make sense? In the private sense, you can have a company with a lot of experience in drilling these wells and installing these downhole observation tools. And then you have the public side that can, collect, analyze, and make that data available to the public. And, being able to have those long-term observation locations all throughout a specific area, looking, at areas that don't have oil and gas exploration, because again, we're really limited on the information that we have in those areas. So, so I think that's a pretty interesting concept, these public-private partnerships. That's actually our poll question that we have. I think Sarah's going to bring up the poll question for people to answer. So do you think that that's a good model for funding this pre-competitive science? Wait for a few more responses. Okay, yes. Wow, 93%. That is overwhelming. So that's excellent. Yeah, that's good. That's good information. So yeah, sounds like that's a that's a good way to go forward. So my final slide, well, actually, sorry, second to final, is really just, again, summarizing how, in my opinion, how important these pre-competitive science data sets are for our general understanding. And, I'm really grateful to the organizations that provide that support. And then, of course, we're not done. There's lots to do: extended gas composition analysis, soil gas testing, produced water analysis. There's just so much to look at. Um, and so before I turn this over to Aaron, I just wanted to mention to everybody that we do have some EMD related events at Image. I hope folks can attend. There's going to be some geothermal talks. We have really great special session, black shales to brines, looking at some of these unconventional sources of critical elements. Geologic hydrogen exploration, that's obviously a hot topic right now. And then some of these integrated sessions on Thursday, characterizing those natural hydrogen reservoirs, and geothermal and critical minerals. So I hope we have good turnout at Image, and that people can attend these EMD related events. So that's all I have. Thank you.
Thank you. That's great. Really excited about it and really appreciate this. Now, we have Aaron via phone, so he'll be talking to us via speakerphone because we've had some technical difficulties. So, Aaron, can you hear us? Yeah.
People hear me?
So, Ashley, can you hear Aaron?
Yes.
Hello?
Yes, I
Okay,
can.
all good.
Okay.
Okay. So we're on your first slide. Aaron, can you see the slides?
Yes. And am I able to control these myself, or I just need to tell you when to advance them?
You'll need to tell us when to advance them.
Okay. All right.
Okay, great. Welcome.
All right. Well, my name's Aaron Ball. I'm the founder of Keystone Geoscience, and I'm presenting this talk, laser-induced breakdown spectroscopy for critical minerals and rare earth exploration. So next slide. So laser-induced spectroscopy is a relatively new form of atomic emission spectroscopy. I became interested in it several years ago when I discovered that NASA was using this technology in its ChemCam instrument suite on the Curiosity and Perseverance rovers, and that this technology is well suited for detecting light elements in samples. So it could be helium, hydrogen, or lithium. And particularly at the time, I was interested in lithium, but this can detect all the elements on the periodic table. So what we have shown here, this is similar to the PXRF that Ashley was showing in her presentation. It's a handheld unit, but the system was originally designed for hard rock, because the laser will create a plasma from the sample. Water or liquids are a difficult thing to sample. So what SciAps has done, what one company has done, is they built a test stand docking station where the handheld device can be docked, and the liquids or fluids are pulled through a pump system and atomized directly under the laser, so that there's a reduction in this spatter that happens that creates a lot of noise in the testing of a sample. So next slide. So this is showing a little bit of how this system works. So we have a rare earth element laser. a neodymium doped yttrium aluminum garnet laser. Laser light travels in parallel waves, unlike the light from a light bulb where it's cast in all directions. So because it is parallel, it can be passed through a focusing lens so that all those parallel rays will converge at the surface of the plasma. And this creates an intense beam right at the surface of the plasma that can excite electrons on the sample. When those electrons are excited, and I'll discuss this in the next slide a little more, they emit light, and that light can be collected through a collecting lens and fiber optic cables and passed across to a digital camera, essentially, a spectrometer and a digital camera. So then that data is analyzed to produce a chart that can be interpreted based on the wavelengths of light that are coming out so that we can determine what elements are there. So go ahead and next slide. So as I said, this could be used for solids or fluids. With solids, this will work for both amorphous and crystalline materials, unlike X-ray diffraction, where X-ray diffraction is really looking at the crystalline structure. This is solely looking at the elements and the wavelengths of light that are emitted. This can be used in a solid form. It can be used to analyze the surface of a solid or to do bulk analysis. So in a bulk analysis scenario, the sample would need to be crushed and pulverized into a powder and then homogenized. Essentially, you're still only analyzing the surface, but you're mixing it so thoroughly that you're getting a representative sample within that mixture. And then these are powdered into a pellet, sort of like with XRF, and then pressed so that the pellet will form out of some sort of binding material. As stated in the previous slides, the system will also test fluids. These can be passed underneath the laser, then atomized into a mist so that the spattering effect doesn't happen as it would with just a stationary liquid. Essentially, this is similar to passing aerosols or dust particles underneath the laser. So any sparking effect that produces spatter is minimized. So go ahead and advance to the next slide. So this is how the atomic emission spectroscopy works, or sort of this theory behind it. So at the atomic level, the laser is focused in on the surface of the sample. That focused laser light is really intense and excites electrons to jump up into a higher electron shell. So we have in this image, we have a photon interacting with an electron, and it enters into an excited state when it does so. Once the laser light is shut off, that energy is still present in the electron, but it cools down. It becomes de-excited, and as that happens, we have to release that energy somehow to go to a lower level of electron shell. And as that happens, a photon of the same wavelength that is necessary for that transition is emitted. These occur in the visible or ultraviolet spectrum of light. So go ahead and advance to the next slide. So here we have the absorption and emission spectrum for hydrogen. And this will be critical understanding a later slide. So the absorption spectrum, what it shows is the full wavelength of visible light, but where the electrons are being excited from, those wavelengths are blocked. So there's absorption taking place in those wavelengths across the spectrum. And we can look at also emission spectrum, which is showing the wavelengths that are emitted from a hydrogen atom after the energy is removed, the energy source is removed. So is as the hydrogen atom is relaxing and the electron drops to a lower shell. So we'll go ahead and advance to the next slide. In these LIB systems, these laser-induced breakdown spectroscopy systems, the laser light that is rather the emitted photons of light that are collected from the source are collected from the sample, are cast across a diffraction gradient, and you get this Eschelogram or Eschel spectrum, where the light spectrum is folded to fit into a small area. And this is important. But as you can see here, there are places along that where there are dark spots. It's not a continuous spectrum. Those are the absorption lines. And so the absorbed spectrum is represented here by those dark spots. So if you go to the next slide, this Eschel spectrum is cast across a computer camera chip, and that allows the translation of the absorption spectrum into an emission spectrum. So those blocked out black areas of light then become a area where on the chip it's active. So if you go to the next slide. So here we have the absorption spectrum at the top for hydrogen, and the lower image shows a typical graph for this LIB system. And what I have highlighted is the hydrogen peaks that occur at the same wavelength in the absorption spectrum are being emitted and creating intensity at the same wavelength in the LIBs that the LIBs is detecting. And so this spectrogram is showing a calibration sample used for calibration of lithium brines with the system that I purchased. And what's showing is the hydrogen peaks. So to show that it can detect those lighter elements, but also because this was pure water, this particular sample was pure water, there should only be in this a very, very minimal matrix effects. So there should be very little noise in the entire spectrogram. And so you can very clearly see that hydrogen is present and oxygen is present. And then because this is passed as a aerosol or a mist beneath the laser, there's necessarily going to be some atmospheric gases mixed in. So we see peaks from nitrogen as well. And yeah, so go ahead and move forward to the next slide. So in this next slide, what I'm showing is I have overlaying a sample from the calibration set that has brine in it. And in particular, this was for lithium brine. So there are lithium peaks as well as some of the other alkaline elements. We'll go ahead and advance to the next slide. We'll put those into perspective. So here we have illustrated lithium, sodium, potassium, and calcium that were all in the calibration set. The lithium peak is, I need to point out, for this particular sample was at 10,000 parts per million. So that was 0.5% of the sample. So that's important to know because as we advance forward in the presentation, we'll see how the intensity for lithium changes based on the concentration of lithium in the brine. But here you can see that this was the brine that was mixed from pure water. There's not a lot of matrix effects, so you're getting clear peaks right where the element should emit light. So if you go ahead and advance to the next slide. So this is showing the 3 of the samples that I analyzed for the calibration for lithium brines. What we have are samples at pure water, which is the red sample analysis. It has 0 lithium in it. We have 0.25% lithium, which is the green line, and then we have a 0.5% lithium, which is the 10,000 parts per million line peak we saw in the previous spectrogram. So what we do here is we take this this interval across this peak and this normalized bell curve, and the peak is taken from that curve based on its maximum. And you can see that the increased density or the increased concentration of lithium in the water affects the emission spectrum. So if you'll go ahead and advance to the next slide. So we take the normalized intensity, and I say normalized because there are some matrix effects, and we have to take those out to get just the effect of the lithium. So the normalized intensity of the lithium is graphed on the x-axis, and then the concentration for each one of those samples is graphed on the y-axis, and that gives us an ability to interpolate or extrapolate along a curve. Let's see. Yes, that's all I have for that slide. We'll go ahead and advance to the next one. So we were talking about lithium brines. That's obviously a fluid. We can use the system also for solids, and something that I've been turned on to and we'll be looking at in the coming months is the Altamaha formation in Georgia. And in Georgia, they've discovered that there are rare earth elements in clays that have been mined for 100 years, many decades anyway. And the gangue of those clays, the dirty grit is what, as it's referred to, it's rich in rare earth elements. And so there's an effort being made within Georgia to go back and look at the waste product of this mining effort to see if we can determine a way to valorize, and then extract the rare earths from these tailings piles. So go ahead and advance to the next slide. So we talked in the brine sample that we showed, where in particular where we had pure water, we showed there was very little matrix effect. There's not a lot going on. In the certified reference materials that are sent, it's a mixture that's got clay in it, as well as it's been doped with or spiked with abundances of the rare earth elements. So you can see the difference in the spectrogram. There's a lot of matrix effects here. And what I have shown are two different samples. One that has a very small amount of lanthanide in it, or lanthanum in it, and the other has a very high concentration of lanthanum in it. The matrix effects are independent of that, but I wanted to show the matrix effects in this. So if we'll advance to the next slide, we'll look at the lanthanum. So here we have the lanthanum calibration curve. I've taken the normalized intensity for 5 or 6 of the samples. The ones that were shown in the previous slide are the end ones, the end tests, the one on the low end and one on the high end. And you can see that the intensity is increasing, and so does the concentration in the collection. So the next step for that particular project is going to be in July. I'll head out to Georgia, collect samples of the Altamaha grit, grind them, put them into pressed pellets, and analyze each one of those across an area and see if we can map out how the concentration changes over the client's land area. So if we'll go on to the next slide. So in conclusion, laser-induced spectroscopy is a new, relatively new emission spectroscopy. It's something that NASA's using on Mars because it will give us the entire periodic table. We can determine, using this, the elemental concentrations in both solids and fluids. It's particularly effective with the light elements like hydrogen, lithium, and helium, whereas there are a lot of other methods that, because for example, the XRF, the density of the nucleus is too small for the system to have an effect. And handheld libs can be used in both the lab and field setting. So next slide. So my company is Keystone Geoscience. We do consulting, doing geochemical analysis. We also do petrography and gamma ray spectroscopy and geographic information systems. And our emphasis right now is on critical minerals, in particular the rare earth elements or in germanium. Thank you. That's all I have.
Well, thank you. That was great, Aaron. Really appreciate it. And I just wanted to mention that we will have a critical minerals special session at Image. There will also be, as Ashley pointed out, geothermal and hydrogen activities. So be sure to attend. It's the end of August, and you get a discount if you are a member. So take a moment to click on apg.org and sign up to join so that you're ready and you get that huge discount. Also, I would like to make it just remind people to join EMD. Again, the best way to do it is to enter your profile and just click that you'd like to join. It doesn't cost anything, and lots of benefits. So we did have 1 or 2 questions that we'd like to get to really quickly. The first question is, what does it cost to run fluid samples with LIB?
I don't know. would you like to pay? For running ICP-MS, I think the standard's about $200 if done at a university. I could do it for less. I haven't set the price yet.
Okay, great. Good to know. So everybody contact Aaron. So a question for Ashley, are you seeing an increased interest in uranium?
Yeah, I mean, that does kind of across the board, I think uranium exploration is increasing. And what's fascinating is that there is a lot of content out there from EMD members that you can find. Like, there's a lot of content on the YouTube channel. And then there's also a lot of great presentations that the past EMD president, Michael Campbell, has put together that are on his website. So there's a lot of good information out there about exploring for uranium.
Well, and that's a really good point. And the EMD does have annual reports, and those are available to download through the website as well, which is exciting.
Exactly, yeah.
Okay, so what are some of the big elements of interest in acid mine drainage?
Oh, that's a good question. Not really my specialty area, but I think anything that would be associated with the majors is going to be, present in those acid mine drainage waste products. So, I can't speak to exactly what they are, but I know that there are many companies who are targeting that because there are critical elements available in those AMDs.
Great. Well, we don't really have any. Oh, okay. So with LIB analysis, how long does analysis take?
Um, per sample, maybe in about an hour.
Okay, good to know.
Most of the time is spent making the report.
Okay, excellent. Well, thank you very much. And Ashley, as our president, are there any last words you'd like to say?
I would just reiterate what you said, Susan. Please join. There's a lot of great people working on all of these minerals that are in the Energy Minerals Division, and it's a really great opportunity to meet them and learn from them. And of course, please, come see what we have at Image. So.
Great. Well, thank you very much. Thank you, Aaron. Thank you, Ashley. Ashley's our president, and Aaron's our president-elect. So see everyone at Image.
Thank you. Bye.
Bye.
Bye.